So we can represent electric potentials pictorially. And the way we do that is to illustrate the electric field. So we drew pictures before to illustrate the electric fields. And so the two are related. So if you look at this image here, it shows an isolated positive charge and its electric field lines. The electric field lines radiate out from the positive charge, and that goes in 360 degrees, right? So that's why we always call them electric fields. The lines that we draw actually represent this. The field is almost like think of a bubble. When you blow air into the bubble, how the bubble expands. That's kind of how electric fields, they expand out from the charge. And so the electric field lines radiate out from the positive charge and terminate on a negative charge. So while the blue arrows represent the magnitude and direction of the electric field, the green lines represent places where the electric potential is constant. And I always mispronounce it. This is called equipotential lines. Actually, I think I said it right this time. Yay. In 2 dimensions. So equipotential surfaces in 3 dimensions, are slightly different. But this is what this is our 2-dimensional representation of that. So these are called equipotential lines in 2 dimension. And it's also used as a noun referring to the equipotential line or surface, depending on the application. So the potential for a point charge is the same anywhere on this imaginary sphere of a radius of r surrounding the charge. This is true for any potential for a point charge given by the voltage. So let me write that down here so you guys can see. So remember that the voltage is equal to the constant K times the point charge Q divided by the radius. So remember that voltage is our potential. All right, voltage. And this is the radius. That's why we label it as distance, but it's really the radius of the sphere. That's why we use the letter R. So it's the radius of sphere if we're considering 3 dimensions, circle if you're considering 2 dimensions, right? And then Q would be the charge. And K is just that constant, right? So then R is really a distance, right? And so it's the same value at any point that is given from the distance R. In other words, if I put R here, right, if this is my R here, well, I don't want to end right on a green line, but let's undo that. So if I were to measure the potential here, it would be the same as over here because it's equidistant, right? Does that kind of make sense? That's why they're called equipotential lines. And so an equipotential sphere is a circle in 2-dimensional view. The way we draw it on paper is the same. So you could imagine this is actually a sphere, right? And we're just looking down in through a cross-section of the sphere, okay? So how does that help us? Well, it's important to note that equipotential lines are always perpendicular to the electric field. So remember, the electric field lines are in blue, right? And the equipotential lines are in green. Does that make sense? So let's just kind of note that so you guys don't forget. So remember the equipotential lines. Oh, that's not a very bright green. Let's try to grab that. Can I grab that? There we go. I think I grabbed it. So, no, I never grabbed it. Dang it. What's going on? What the heck? There we go. Got it. That's the color we want. That's what we're doing. We'll make it a little darker. Okay. Why won't it let me draw? There we go. So the green lines are equipotential lines, and they're always perpendicular to the electric field. So let's write that down. So I'm going to say the lines, and then those are always perpendicular to our blue electric field. Okay. And so it's important to know that they're perpendicular to each other. No work is required to move a charge along an equipotential, right? So, in other words, if you move something along the equipotential line, there's no work that's required. So we'll write that down. Delta V equals 0. And that's because no work to move charge along an equipotential. Okay. So then now we're going to start deriving some formulas. So remember that work is equal to the negation of the change in potential energy, and also that is equal to the charge times the change in voltage. And then we're saying that this is equal to 0 because no work is needed. Since the force, so remember the work is 0 if the force is perpendicular to the motion. So the force is the same direction. If the force is the same direction as E, so the motion along the equipotential line is perpendicular to E. More precisely, we would write it like this. Work is equal to F times the distance times cosine of theta, or the charge times the magnitude of the field times cosine, or times the distance times cosine of theta, but again, it's still equal to 0. Okay, so this is the work related to the electric field. Note that the above equations, E and F, symbolize the magnitudes of the electric field and the force, right? So you guys should know this by now, but we'll label this. Remember, this is the force, and this is the magnitude of the electric field. That says electric field. Canvas struggles to keep up with me. I write pretty fast. And so neither Q nor E nor D is equal to 0. So cosine of theta must be equal to 0. So I guess so we're thinking, in other words, this will have a value, this will have a value, this will have a value, this will have a value. So the only thing that zeroes this out is cosine of theta. So what we're thinking about is what values of theta makes cosine equal 0. And so one in particular, cosine of 90 degrees equals 0. Okay? Or 0 degrees, I suppose. But okay, So one of the rules for static electric fields and conductors is that the electric field must be perpendicular to the surface of the conductor. This implies that a conductor is an equipotential surface in static situations. There can be no voltage difference across the surface of the conductor, or charges will flow. Once one of the uses of this fact is that a conductor can be fixed at 0 volts by connecting it to the earth, and with a good conductor, the process is called grounding. Grounding can be useful as a safety tool. For example, grounding a metal case to an electrical appliance ensures that it has 0 volts relative to the earth. So a lot of electrical things have a secondary ground just in case the primary ground fails. So I'm gonna type that. I want you guys to write that down because we're gonna start doing circuits, and it relates to that. So I'll just jot this down. Too big. A conductor can be fixed. Well, let me make it bold. All right. A conductor can be fixed at 0 volts by connecting it to the ground or earth. And so that kind of eliminates the potential because the electrons will take a path of least resistance to the earth. The earth can soak them up. Okay? Moving forward, because the conductor is an equipotential, it can replace any equipotential surface, similar to that first image. A charged spherical conductor can replace a point charge, and an electric field and potential surfaces outside of it will be unchanged, confirming the contention that a spherical charge distribution is equivalent to a point charge at its center. So I'm going to show you a new image here, and we'll talk about this. And so in this figure, it shows an electric field and equipotential lines for two equal and opposite charges. Okay, given the electric fields, the equipotential lines can be drawn simply by making them perpendicular to the electric field lines. So, in other words, if we're building on our electric field stuff, so we know from drawing our electric fields that this is how, if we look at the blue lines, we know that the blue lines are electric fields, and so to construct our equipotential lines, we're just going to make sure that it's perpendicular. In other words, the green line, wherever you see the green line intersect a blue line, it's perpendicular, and that's how you get the shape. So you start with your electric field lines, and then you draw your equipotential lines such that they're at a 90-degree angle with your electric field lines, okay? And so once you construct that, the electric field lines and the equipotential lines are equal but opposite for the two equal but opposite charges, and the equipotential lines can be drawn by making them perpendicular, right? I just said that. But the important thing to know that I didn't mention is that the potential is greatest or the most positive near the positive charge and the least negative at the negative charge, okay? So when we get really close to the negative, this would be considered the least potential, right? In this area here, this is, shoot, it won't let me. This is like the least potential. And then this would be the greatest potential. And, oh, I hate when that does that. All right, let's see if we can erase that. Boop. All right, let's see if that stays gone. Yeah. And so least would be, another way to say that is most negative. And this would be the most positive. And so let me put some numbers to that. I'm going to put another image up here. That way you guys can see. So in this image, if we put some numbers to it, this is what they're talking about. Okay, so to the right in figure B, I have electric fields. These are two like charges, and this is, we know from our work in electric fields what that would look like. They're going to repel, and this is the pattern of behavior of the electric fields. And so to construct our equipotential lines, we're just going to make sure that they're perpendicular to the electric field lines. Okay, and so because these are negative charges, the electric fields are going to go to the negative charges. However, except, obviously a negative and a negative repel, so there's nothing inside here. And in order to keep this perpendicular, this kind of dips down here, this kind of dips down here, but it can't go too far. Okay. So in figure A, basically the equipotential lines must be measured with a voltmeter in a laboratory experiment, right? And then we would see that this is 10. This is what they mean by the most negative. So don't forget about these little lines right here. So it's negative 10 volts here because it's a negative charge. And then as you move further away, it's negative 5 volts, right? And then as you move further away from that, it's negative 2 volts, okay? And so the corresponding electric fields are found drawing them perpendicular to the equipotentials. So basically they're saying you could draw the equipotential and then do the electric fields, or vice versa. Until you get comfortable, I would do it the other way. I'd draw the electric fields first and do the equipotential, equipotential lines, but at some point you'll need to go in the other direction. But one of the most important cases is that familiar with parallel conducting plates. Between the plates, the equipotential lines are evenly spaced and parallel. The same field can be maintained by placing the conducting plates at the equipotential lines. And let me give you an example. I'll show you real quick. So this is very useful in modern day electronics. Right? We couldn't do anything without this. And so an important application of these electric fields and equipotential lines involves the heart. The heart relies on electrical signals to maintain its rhythm. The moment the electrical signal hits the chambers of the heart to contract and or relax, when a person has a heart attack, the moment these electrical signals are disturbed, an artificial pacemaker goes in there and actually takes the place and makes sure that those charges, those electric signals go through in a rhythmic fashion. And so basically you have to open one chamber and close another chamber, and they have to be in sync. And that's how the heart pumps your blood. So a pacemaker actually does that. And that's basically it for the notes. I'm going to do one more thing on the notes. I'm going to pull up the charges and field again. And this is all building, we're ramping up to capacitors, and capacitors are ways to store energy. Remember, voltage is the potential. And so if we want to be able to store energy, and so this is one of the ways that we can actually store energy. So I want to pull up this simulator, and we'll call this a day. Not a lot of math here. The next section will have some more math, but Let's just do this. I want to do the charges. Charges and fields. So this is not new. We did this before. I think we did this before with just the electric field. So in other words, if I put a charge up here, those are my electric fields, right? And I put an equal but opposite charge, we kind of have this pattern, right? Now if I want to show the potential, there's a potential between these two, right? So I think this is 1 nanocoulomb positive, and this is a negative one. And if I really stretch this out far away, notice that my voltage changes as I go through, right? See how that changes as I go through? And so let's recreate, what was the one? Let's try to recreate this one right here. So I'm going to do 2 negative charges. How about that? So I'll do the 2 negative charges. So let me get rid of this one. Boink. Oh, I got to start over. So I'm going to put a negative charge here. I'm going to put a negative charge here. And then I'm going to show the voltage. And so this is the most negative, right? The closest that I get to either charge, and it's going to be negative and negative. I'm never going to have a positive voltage here. But we said, and I don't know how close we need to be. Let's put them a little closer together. They said that you could get like 5 volts. I think I need to move it further away. Yeah. So right here, you have your least potential, right? Because of where the electric fields are. But remember, there's an electric field that kind of goes right around here. So if I measure my potential here, you know, it's like negative 36 volts. But as I move further away from the charge, it's like negative 9. Okay. And this sensor just kind of shows us some things here. If I wanted to show some values, I wish I could get rid of that. I can't. I'd have to redo the whole thing. But basically, the equipotential lines are a way, as basically what I want you to try to visualize is that these green equipotential lines represent, in other words, the spacing. As you get further away from the charge, it changes the voltage. Okay. And this 2 volt thing is going to go around this outer, in other words, I've got 2 charges here, right? This is very high. But if I get far enough away, this is like 6 volts, and I get almost like an oval around here. It's 6 volts, 6 volts, 6 volts, okay? If I get closer, I can kind of go around here, 11 volts, 11 volts. It's pretty much equidistant from the charge. If I go over here, it's 11 volts, 11 volts, pretty much equidistant. But if I go over here, it's not 11 volts, okay? Because as we get in between the 2 charges, there's some wonky stuff that goes on, okay? And so that's just like this image here. Based on these charges, this space here is like negative 10 volts. This space here would be like negative 5, but if you go out further, it's negative 2. And that's it. That's all we're trying to do. We're not going to do a lot of calculations today. But you do have homework.